Good morning. All right, lesson 12.4, conditional probability. All right, the last of 3 lessons to close out probability and to close out the school year. So you made it. Yay. All right, anyway, what we're doing today, conditional probability. What it really is that you're finding probability on a more specific part of the information, like you're isolating by another factor. It involves usually using these two-way frequency tables that we used in the last lesson. It's not hard, it's just remembering kind of a formula and just kind of concentrating when you do the probability. So it'll all fall into place. Unfortunately, I usually do this in class and we make our own two-way frequency chart, and it's a lot of fun. A little bit more interaction, but we're gonna have to go for it just the good old-fashioned way because that's our only choice right now. All right, so anyway, here we go. Example 1, we have our two-way frequency chart. We saw it in the last lesson with going to college, not going to college, male or female. Okay, so we have 52 graduating seniors. They're surveyed and their information is separated into, males, females, going to college, not going to college. All right, so real basic probability in A and B. We're just going to figure out if the person was picked at random, find the probability that the person was female. All right, so part add a whole. Your part is the female, the whole is the whole graduating class that was surveyed. So let's see, the number of females total would be this 22. Out of that total number is that bottom corner, the 52. And a lot of times, we're going to leave it like this. You could turn it into a decimal. You don't have to. When you're making comparisons, you're going to want to change it into a decimal. It's a lot easier to see what is bigger or what is smaller on the decimal value than the fraction. All right, so let's take a look about how many kids are going to college. Okay, so just the idea of going to college would be this row right here. A total of 29 of those graduating seniors are going to college. That total that were surveyed was 52. Okay, so nice basic probability, easy peasy. All right, now part C is going to introduce the new part of today's lesson, which is the conditional probability. So now we're going to base it on a smaller part of that chart. So letter C says, what's the probability of going to college given that they were female? All right, so now what that is saying is isolate just purely by female and tell me the probability that if you're female in this chart, going to college. Now, you can do a Venn diagram, okay? Let's kind of talk about Venn diagrams. It's been a while. We have the idea of female going to college. So this whole circle here would represent the total number of females. This circle here would represent the total number going to college. This little middle intersection are the females going to college. So the idea is when you're filling in a Venn diagram, sometimes it's easier to fill in the middle and work backwards. So if we look, right, this little section is female going to college. That's that number 13 up here. So I'm going to fill in 13. And I know that this circle represents the total amount of females. All right, the total amount of females is 22, but 13 of them are already counted here. So 22 minus 13 leaves you with 9. So this whole circle, these two numbers should add up to all the females, and they do. That's 22, 22. Same idea with going to college, right? Going to college would be 29, of which 13 are already counted here. So 29 minus 13 is 16. That will give us our whole 29, okay? All right, so now what we want to do is we want to do the probability that you're going to college given you're a female. So the number of females is going to be that whole part. So the number of females would be 22. And out of those 22 females, how many are going to college? Well, that's that little number here, 13. So now we've just isolated it, made it a little bit smaller, okay? So with that, let's talk about this idea here, which is more likely that a person at random will be going to college given they're a male. So I'm isolating by males, taking the number of males and seeing how many are going to college. Or is it more likely that the people going to college are male? So let me say that again. This first guy, the probability of they're going to college given their males, means I'm isolating the male population and I am figuring out how many are going to college. If I flip it, it says what's the probability that you're male given you're going to college. So now I'm isolating out of all the college students, okay? So let's hit this one again, this first one. The probability that you are going to college given you're a male. All right, so you're isolating out of the males. So the males is going to go on the bottom. Right, that's your whole part. So let's see, there are males, there's 30 going to college. I mean, not 30 going, but there's 30 total, okay? Now, the males going to college. So the ones that are going to college that are male, so now I'm isolating it. That's 16 out of the 30. And that's your probability, okay? So number of males going to college, let me do that. All right, this guy here, right, we're gonna isolate by the number going to college in general. Okay, and then we're gonna isolate by the number of males going to college. So same thing, it's gonna be the same top number. So it's really a comparison. So the number going to college, that's your 29. That's going to be your bottom number. And out of those 29, 16 of them are male. So the top number stays the same. The bottom number is what's going to change. It just, it differs in what you're isolating by, okay? So again, we're going to extend that. We're going to look at this crazy Venn diagram on the second page with a bunch of dots. So it's kind of like a vague case. So let me just make sure we're in view here. All right. And the camera focuses. Come on, camera. Okay. So example 2, we have a generic Venn diagram. We have no idea what it's talking about. We've got dots inside. We've got dots outside. Some of them fall in event A, right? So anything in here is event A. Some of them fall in event B. Here, this in the middle are the number that satisfy both A and B. All right, so what we're gonna do is we're gonna figure out some probabilities. All right, we are gonna consider the probability of A occurring given that B has occurred. Okay, so now I'm gonna really go back to doing your formula. Okay, which we didn't go into basic detail, but I wrote it out in words before. It was a little easier to see when it was a real life example. But when you have something vague like this, all right, when you are doing the probability of A given B, the formula is you take the number in A and B, so that intersection, and then you divide by the number of whatever that second piece is. All right, so now we're just counting in this Venn diagram. The number that satisfy A and B are those 4 dots right in the middle. So that's going to be your top number. Now, the number in B is the number in the total circle. So we have these 4, then we have 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 total elements in B. The probability that given B you satisfy A is going to be 4 out of 12. If you want to reduce, 1/3. Okay? So you're going to have to remember the formula. It's not that bad. Again, if you are looking at this formula in general, okay, talking about probabilities, okay, the ends were easy here because we had that information, but sometimes they refer to it in probability, like the probability of something happening. So if you have conditional probability, which is the probability of A given B, the official formula is the probability of A and B divided by the probability of whatever's listed second, so the probability of B. Okay? So that's your general formula. Conditional probability we are going to use in the next lesson, so you have to memorize it. It's something new. You've never seen it before, but it's really not that difficult. So one last problem using a two-way frequency chart. We're talking about hair color. We're talking about eye color. All right, and then we're going to isolate, and we're going to do some conditional probability. All right, so your options for hair color: black, blonde, and red. I'm assuming that brown falls in the black category. I don't know. And eye color: blue, brown, and green. All right, a little known fact. It's actually funny because I consulted Dr. Gatz. I don't know if any of you know her. What about if people have hazel eyes? You know, people say my eyes are hazel. Hazel actually falls in the blue category. Believe it or not, it's not what you would think. I would think it would be more towards green, but actually hazel is brown. Not brown. Ugh, such an idiot. Hazel falls under the blue category. And I actually had Dr. Gatz come in a couple years ago and explain why. All right, anyway, let's take a look here. We are in part A. We're finding the probability that the person picked had brown eyes given they had blonde hair. So if you're going to write it out, it's the probability, right, of the first condition. Brown eyes, given is that line, and then blonde hair. So according to the formula, right, which is right up here in words, it's the probability that you are brown eyes and blonde divided by the probability you are blonde. Okay, so we have the probabilities in here. We don't have actual like numbers of people that fell in there. All right, so the probability that you are brown and blonde. Brown eyes, blonde hair. It looks like 0.10. That's going to be your top number. On the bottom, probability that you're a blonde. All right, blondes are here. Total number of blondes, 0.35. This one, I would hit up my calculator and simplify just so I had a better idea of the number. And you're going to get 0.29. And what that means is, ready for this? 29% of the blonde-haired people have brown eyes. That's what it's saying. That's the probability that you have brown eyes giving you a blonde hair. So if I isolate all those blonde hair people, 29% of them is the probability you would have brown eyes. Okay? So again, with probability, my biggest issue is that probability is so tricky. And it's all in the way you read it. You have to read it so carefully and so literally. All right? But with conditional probability, although it's new, it's pretty straightforward. You have a formula. Okay? So here, let's take a look here. Letter B. Find the probability that the person had red hair given they have green eyes. All right, so here's my write-up, which means I'm going to do the probability that you have red hair and green eyes. All over, I'm segregating out by my green-eyed people because that's what's listed second. All right, the probability that you have red hair and green eyes. That looks like 0.15. Over the probability you have green eyes, that's 0.25. Which is, look at that, 0.60 when you type it in the calculator. All right, so 60% of the green-eyed people have red hair. So that's pretty telling that a lot of red-haired people do have green eyes. Wow, interesting. All right, so last question. Does having red hair seem to have some dependence on having green eyes? All right, let's see. How can you tell? All right, so the probability of red hair giving green eyes, right, is 60%, which we just had. Red hair giving green eyes is 0.60. And the probability that you have red hair just in general is, let's see, probability you have red hair is about 20%. So yeah, I would say it's really high. It's really likely that if you have red hair, there's a really good chance you're going to have green eyes because it's 60% there. Okay, the probability you have red hair is only, is 20%, but it's really high if you have green eyes as well. All right, so that letter C is going to carry into our next lesson. So we are done with 12.4 and moving on to 12.5. All right, have a great day. Enjoy it. The end is almost near. You're almost done, so don't give up. All right, be good.